Okay, should we get started? Okay, can someone lock the doors, please, so no one can leave? It's being sorted out. Thank you so much for coming along today. This is actually one of my favourite conference venues in the world, which is weird because it doesn't, on first glance, seem like a great venue, but I love the sort of brutalist nature of it. I also not sure how I feel about all the high-intensity security downstairs as well. Believe me, it's been worse in past years. But you are also fortunate enough to be enjoying what I think is typically the best conference food that I see at these venues, which doesn't say a lot, but says quite a bit, actually, because the staff here work really, really hard. And I had a good coffee earlier. So I'm already buzzing and I'm already happy. So it's good to see you all here today. We're going to be talking today a little bit about meaning. What words mean. So I'm going to be doing this, I didn't set out to do a talk about meaning. I set out to do a talk about trying to clarify some concepts that we talk about a lot. I spend a lot of my time working with clients all over the world looking at their architecture. Typically the way I'm working is how do people and architecture and technology all work together. And that's ended up being a big focus of my career, really for the last 25 years. In hindsight, that's what I've been doing. And I spend a lot of my time as part of this thinking about boxes and arrows. We often joke that we can break architecture down to boxes and boxes and arrows are very much a major focal point of what I do. And sometimes we're thinking about how big those boxes should be, or more importantly, how small those boxes should be. Sometimes we get to have more interesting conversations, like what should we put in the boxes? And maybe the boxes should be broken up into smaller boxes using cutting-edge ideas from the 1960s. I tend to often focus on the right shape of the box, and of course, the correct shape of a box is a hexagon, in case there was any doubt. But this is not going to be a talk about the boxes. This is mostly going to be a talk about the arrows between them. And often when we're thinking about how we find the boundary of a service, for example, how that maps to organizations and team and work, and that's all very, very important. But then we get into the conversation is, okay, great, Sam. Now, how are these boxes going to talk to each other? And that's what I want this talk to be about. Now, obviously, I spend a lot of my time thinking about microservice architecture because I'm nothing if not able to surf every single buzzword until it's no longer valid. But this is the kind of architecture diagram I draw a lot. I draw boxes and I draw arrows. And typically when I draw an arrow, what I'm denoting is a dependency. So I'm going to try and be very explicit about meaning in this talk. For some people, these arrows mean different things. When I draw an arrow between two boxes, I'm showing some form of logical dependency. So in this example here, where we see a returns having an arrow talking to shipping, I'm not talking necessarily about the flow of data, because data always ends up flowing in both directions. I'm talking about a logical dependency. From a logical point of view, the return service has a dependency on the shipping microservice. That's what I'm just explaining with these arrows. And so at a high level, this is all fine. Where it starts getting more confusing is when we start wanting to talk in terms of these arrows being synchronous arrows or asynchronous arrows. Now, I've kind of tried dealing with this issue a few times over the last 10 years or so, and I've never been entirely happy with the distinction here, but I kind of just shied away from it and hoped that somebody else would sort out this distinction for me. And that hasn't happened. But while I was not dealing with this problem, and I sort of just batted it away, instead I'd focus on a distinction which I think is much clearer, and that's the distinction between request-response-oriented communication and event-driven communication. Because when we're thinking at a higher level, when we're thinking at sort of a logical level, this distinction, I think, is clear and has some very different type of outcomes when we think about the working relationship between services. Talking about request-response-based software, or just request-driven interactions, this is really, really straightforward. And I think this is a familiar pattern to most of you. You have a service, the return service, which is going to ask for something. So returns depends on shipping, and the way that dependency is implemented is the returns microservice is going somewhere and saying, hello, shipping service, can you please provide something to me? So I'm making a request. Now, I know some people like using the word command. I prefer request. Words are important, as we'll see later in this talk. The reason I prefer the word request over the word command is because request seems slightly softer. A command is something that must be obeyed. On the contrary, I think actually you should be able to say, no, the thing you've asked me to do is not valid for me. So that's why I prefer the terminology of request. I also like using this word because the term request is in the HTTP specification, and that is the best and most widely used kind of interprocessing abstraction layer that many of you are familiar with. But this example here, we've got returns microservice. I'm sending a request. I'm asking for something. And I'm getting back a response. Sometimes the response is, no, I can't help you. Sometimes the response is, yes, I can, and here's what you asked for. Sometimes you don't actually want anything back other than an acknowledgement of receipt. We would often talk about the returns microservice here as being the consumer. I am consuming functionality provided by the other service. And I think this is a pretty clear-cut example or a high level of interprocess communication. We'll talk a bit later on about the different ways we can implement this in terms of synchronous and asynchronous communication. We've then also got event-driven communication, which is very different. With event-driven communication, there's an inversion. To an extent, it might be considered a passive-aggressive form of communication. Here we're dealing with facts. Facts. Something has happened. In this case here, the inventory microservice is firing an event to let us know that we've just received 10,000 copies of Justin Bieber's greatest hits. This is important information that the system needs to be made aware of. We have two different services, the promotion service and the wishlist service. From a dependency point of view, you might show that promotions and wishlists both depend on inventory. They want to know when stock level changes. But the way we implement that dependency has been inverted. Now they consume the event. Promotions and wishlists, two different services that want to do different things with the same piece of information. It could be great in broadcast situation. The promotions microservice, for example, may well start discounting products based on the fact we've now got way too much Justin Bieber. On the other hand, the wishlist microservice might say, well, there's all these people, all these believers out there that want the latest copy of Justin Bieber's greatest hits, and they need to be alerted. And so we kind of, the consumers here are on the right side. I personally love event-driven systems. I always found they're nice and loosely coupled. It also gives you fantastic ways in which to really screw systems up. We're not necessarily going to go into detail about the distinction between request response and event-driven today, but I wanted to lay out the landscape where I think this distinction is pretty clear on the whole. And most non-trivial architectures I've worked on have a mix, and that's absolutely fine. But the reason I've focused on this distinction is because it is easier and clearer for me to explain, and yet when I come back to wanting to talk about this distinction, synchronous and asynchronous, that clarity is not there. The distinction between synchronous and asynchronous, which is by far and away the thing that most people want to talk about. Should I use asynchronous communication? This is where things get a lot more murky. And in the past, I would say, well, look, when you're doing request-response-based communication, you could do synchronous or asynchronous. When you're doing event-driven communication, it's mostly some kind of asynchronous communication. And then I would just hope that people would go away after I said it depends a lot. And I'm getting older. I'm realizing that I should probably address some of my past traumas. So this is part of what I'm trying to do here is, look, let's take another run at this. Now, unfortunately, I don't think I've quite solved it. But I have come up to the conclusion of there is no consistent definition of what asynchronous communication means in the context of interprocess communication. It does not exist. There is no consensus. There is no useful working definition on which we all agree. And therefore, we should probably stop using the word asynchronous. I was actually inspired to do this talk because of this blog post. This is a post by Pat Helland, one of the pioneers of computing. He's got a great Substack. I have views about Substack, which we'll leave till later. But his newsletter is great. And in this post, Pat Helland is trying to review the use of the term consistency in eventual consistency. And he argues that the term eventual consistency is confusing because of the word consistency. We use the term consistency to mean different things in different spaces in computing. Ironically enough, consistency is not consistent. Consistency in the context of an ACID database transaction, for example, has extremely clear mathematical properties, and they are probably not what you think they are. And so as a result, when you see people working with database transactions and working with eventually consistent systems, they get themselves in a mess because they somehow think they're sort of similar, and they're not, they're totally different concepts. He's actually arguing here that we should instead talk about eventual convergence, because with eventual consistency, it basically states that we will see consistent views once all replicas process all the messages. Eventually, our replicas will converge on a consistent view. So I was hoping, maybe I'm as smart as Pat Helland. I am not. And perhaps I can do for asynchronous communication what he attempted to do when redefining what eventual consistency means. Could I come up with a new word? I did not, but I discovered a lot of things along the way, and I'm going to share them with you. Now, because I am obviously a highly experienced researcher, I went immediately into full-on research mode and sent a tweet out. And just hope that other people do the work for me. And so I said to the people that followed me at the time on Twitter, I said, hello, everybody. I think there's confusion about what asynchronous means. And I just wanted to see, in a deeply scientific way, that I absolutely haven't cherry-picked to fit my narrative, what exactly do people out there think that asynchronous means? So maybe it won't shock you to find that there was divergence. I've kind of given away the ending here. One of the first responses I got was from an old colleague of mine, Darren Hobbs, and he said for him, asynchronous communication is the difference between, say, sending an email versus having a phone call. Okay, that's interesting. I sort of liked that initially. There is an immediacy that when I pick up the phone, we have the conversation, we're going backwards and forwards. And we often, in the context of work in, say, an office environment, will talk about email being more asynchronous and face-to-face conversations being synchronous communication. So in the context of human interactions, this kind of feels true. However, when we start thinking in the context of computer-based systems, this distinction starts feeling interesting because it kind of implies that asynchronous communication will somehow be slower than synchronous communication, which is just flat not the case. The lowest latency systems that I've worked on have all been asynchronous. So there's something here, but it doesn't feel right. As an analogy, as a metaphor for asynchronous communication, it doesn't quite do it for me. But there's something interesting there about the immediacy. So while the Twitter thread's going on, I did a little bit of research. And I started looking for definitions out there from smart people. Because I am not a smart person, but I have Google, so I can therefore cherry pick smart people's information. And so I took a look at the Reactive Manifesto. Now, how many people here have read the Reactive Manifesto? A few of you. Okay, all right. So the Reactive Manifesto is written by some smart people, many of whom I consider to be friends, and from whom I've learned a lot. It is also an example of what I would describe as dogma, which is a very opinionated set of views from people who position their views as being the only way forward. It is also a deeply confusing and flawed document. And that is, I want to be really, really clear here, there's a lot of hard work that they put into trying to make this document clear, and the latest version is much better than the original version. However, you don't have to go very far to realize it's not actually useful in terms of helping us understand how to implement systems in a number of different ways. Let's start by looking at the term asynchronous. We go straight to the nub of it. So, asynchronous communication. Please tell me, smart people, what do you think asynchronous means? And they said, in the context of this manifesto, good, they're talking about context. Context is important. We'll come back to context later. In the context of this manifesto, we mean that the processing of a request occurs at an arbitrary point in time, sometime after it has been transmitted from the client to the service. That's very clear. You're thinking, well, Sam, that's extremely clear. Why can't you understand this? Let's take another run at this. The processing of a request occurs at an arbitrary time, sometime after it has been transmitted from the client to the server. As opposed to what? Right, as opposed to us processing the request before it was sent. Is that, because that would be the opposite for me, right? So that would be synchronous communication, that I'm going to process a request before it's being sent. Like we've got some sort of time travel type networking protocol going on. So that's not helpful, because we always process something after it's been sent, because that's the causal nature of our universe, or at least that is the causal nature of our networking protocols and computer infrastructure. There's other stuff in here that is getting closer, I think, to at least what some of the authors of the manifesto think. And by the way, I've spoken to enough of the authors of the manifesto to know that they do not all agree. But that's okay as well, because this is also about disagreement. As I said, writing this is really, really tough. And I want to be really clear. I am poking fun a little bit, but I'm poking fun at people that have put a lot of hard work in, and there is still valuable stuff in here. But there is more of a helpful definition in here. So let's take a look elsewhere in this section. So they go on to say that this is the opposite of synchronous processing. They use a different word there. This is the opposite of synchronous processing. And they're saying that synchronous processing implies that the client only resumes its own execution once the service has processed the request. Now, this is kind of interesting. So around this time, I got some more responses in my thread. So I got a comment here from Steve Smith. Steve works at Equal Experts. He's an old friend of mine. He's very tall, very smart chap. He said that for him, communication between asynchronous communication, or synchronous communication rather, means that the TCP connection is open for the duration of the communication. And I sort of knew where Steve was going, but I wanted to poke fun. So I said, okay, well, if I'm using a different networking protocol, does that change your definition? And he further clarified to say, well, actually, he's assuming you're not blocking for a response. Now, this is useful. Let's get into terms that are more explicit. This comes back to what the Reactive Manifesto said. I'm not blocking for a response. That's fundamentally what the Reactive Manifesto said. The client is not blocking, waiting for the request and the response to be handled. So this, we've got an explicit term for. This is non-blocking. And non-blocking is cool. Let's take a look at what non-blocking is and understand why it's useful, and also look at some of the limitations of non-blocking. We've got a very simple interaction here. We've got one service, enrollment, which is going to ask both loyalty and subscription to do something. For the purposes of this exercise, these operations can be carried out in parallel. There's no obvious interaction between them, but we both want to make sure these operations are actually completed. So enrollment is going to go to the loyalty service and say, please could you award some points, give some points to Sam. Sam earned some points. Can you also go to the subscription service and please upgrade that subscription so Sam can earn way more money in the future? Now, a very simple way we might implement this, if we're coming to this at the beginning, would be to write it as a piece of code on our client. So inside the enrollment service, we'd have, okay, loyalty service.award points. We could imagine this is maybe some kind of RPC abstraction over the network call that's happening. So we're going to open a connection, we're going to send some bits and bytes asking, that's our request, and then we're going to hopefully get a response coming back over the same network connection. So in this case here, we're going to get a response, res1, is going to be the results of that first call. And so once we get back that response, we then move on to the next line of execution. And so if it completes, we then go on to the next line and do the second thing. So we would describe these as being blocking calls, because from the point of view of the client's code, this thread is basically blocking execution while we wait for the other service to respond. So I'm going to wait. OK, now I can carry on. Now I'll do my next thing. Now, one of the problems of blocking calls here is how it relates to latency. If we're looking at the operation, the overarching operation here, our latency is now effectively going to be bound by the sum of these calls. So if we said that the award point call took 50 milliseconds and upgrade subscription took 150 milliseconds, our total operation length, assuming this was the only thing involved, would be 200 milliseconds in total. Now, that's kind of not great, given that we know we could ideally parallelize these operations, but also do bear in mind that latency will vary. You'll typically look at latency on a histogram. And what you'll start seeing is if you're getting lots of calls sort of being done sequentially, you'll see a larger overall variance in the latency of operations, which leads to more inconsistent service behavior, and you tend to try and avoid that. So things like tail latencies and things can get harder to manage in these situations. That's a topic for another talk, though. But an obvious improvement in this situation, because those two things are not causally linked from a logic point of view, would be to actually have those two calls done in parallel instead. So rather, why do one and then wait before doing the other? Instead, can we just do them both at the same time? And we've always been able to do this. But for a long time, it was more things that we would have to handle ourselves until we have this lovely syntactic sugar that we've all got in our programming languages now, typically comes in the form of what we might call reactive extensions. Don't get me started on the number of different ways we've overused the term reactive as well, but putting that to one side, the reactive extensions have enabled operations like this to be done much more effectively and efficiently. So in this example here, I'm wrapping these executions in what's called a future. So a future is a read-only type, the value of which will only be known at some point in the future. And I'm sort of keeping this fairly language agnostic, but what's inside the parameters, the parentheses here for that future call, is basically going to be packaged up and probably stuck on a background thread of execution that whatever reactive extension library we're using is handling for us. So what happens now when we run that first line of code, all that's happened is at the point that the next line, that the program flow flows onto the next line of code, the call hasn't necessarily happened, but we just created that background thread, and that's probably now running in parallel behind the scenes. So now we get close, probably pretty parallel operations. And there's all sorts of different variances in terms of your runtime, exactly how this is done. But the upsell here would be, well, great, we're now doing these two calls in parallel. We would imagine the overall latency of our operations to have gone from 200 milliseconds to 150 milliseconds, and that's great. The issue, though, with non-blocking is request response. We often want a response. Now, sometimes we want the response just to know if it happened. Sometimes we want a response because actually there's information coming back that we might need. It might be the answer to a question. We may have created something and we get back an ID that we then use for further processing, for example. So in this situation here, if we're thinking about reading the program as a human being, that first line of code executes, the second line of code executes. At this point, we do not know if those calls have actually completed or not, because they could still be running in the background. So we don't know if the calls have completed, we don't know if they're successful, we don't know if we've actually got a value back from these calls. So if we do need the results, what do we need to do? We have to wait. So how do we wait? Well, we do something like this. I sometimes see people say, oh, I'm doing non-blocking calls, and they're doing async await. You might as well just delete the word async and delete the word await because you're just doing a blocking call. This blocks. This will block the process flow until both those futures have a value. Now, obviously, there's other stuff we'd expect to see in a real program around retry operations and all those sorts of things. But at the heart of it, if you need the results, you're going to have to wait somewhere. That's just life. Right? So fundamentally, the logic of how your application or your service is set up may still require that you have to wait for things to happen. Even non-blocking calls may end up with you having to block execution on the client. This is not, by the way, me saying you shouldn't bother about non-blocking. You absolutely should, but you should understand it only takes you so far. Sometimes you can restructure processing to avoid problems like this. But if you can use non-blocking, it's still a good thing to do. Beyond the fact that often the syntactic sugar, I think, is really useful, it just actually helps us with latency, and all that kind of stuff is a good idea. So let's go back to the Twitter thread. What else is happening out there? Here's Graham Lee. Worked for many years at a company called Tyro in Australia, which is like a payments company that became a bank. And Graham said, the definition I've been using is that the sending service doesn't wait for completion of the receiving service before continuing and or completing its own work. That first sentence is very much the non-blocking part of the conversation we've already looked at. The second piece is kind of interesting that comes from Graham. It says, now I think about it, I also expect a temporal decoupling from the receiving service's availability. Temporal decoupling is actually a term that is used in the context of interprocess communication. It's also used in the context of just code, and it means different things in different places, which is, again, another example of us using the same term to mean different things, but we'll get into that in a minute. Likewise, we had Benjamin Johnson here saying that synchronous communication for them was a direct communication between the sender and receiver. And async communication, there's an intermediary that's involved in the sender and receiver, for example, a message broker. So for at least Benjamin's point of view, this is about an intermediary. And that's actually what Graham was talking about as well. I'm going to use an intermediary to remove the temporal coupling that might otherwise occur. So we'll talk about temporal coupling in a minute, but we should talk just firstly about this idea of an intermediary. Something between A and B that's somehow going to help with the communication. And the most common form of intermediary we'd encounter in this environment would be a message broker of some sort. Lots of different varieties of message brokers. I'm not going to get into the details of those now, but you've probably all seen or worked with them. But they all work in this context, they all work in a similar way. With a message broker, what we've got going on here is we're sending a message generically between two things. I use the term message as the generic thing I'm sending. It could contain an event, it could contain a request, it could contain a response. That's kind of by the by. So rather than A talking directly to service B, you go via the intermediary. The problem we're trying to solve here is, if I want to send something to B, B has to be there to receive what I'm sending. If B is not available or not reachable for whatever reason, that communication is going to have a problem. That's a temporal coupling we've talked about for a lot of our normal, say I'm saying a normal HTTP call, you have to be there for the request to be processed. If you're not, we have an issue. So temporal decoupling is basically removing the reliance on the recipient being there at the time you send the request. So temporal decoupling means something quite different in code contexts. So how do we do that with a broker or an intermediary? We use them to hold on to the message for us. So I want to send a message to you. I send you the message. The broker now holding on to that message. Great. If B was already available, the broker would deliver that message straight away. And some of these message brokers can be screamingly fast, like eye-wateringly fast. Some of them can also be slow, right? Depends on your appropriate technology you've picked. So we've now removed that temporal coupling problem that Graham highlighted. And what we've effectively done here is we've offloaded some of the requirements around guaranteed delivery. So if I'm just using, say, a normal TCP connection, and I try and send something to you, and I don't get an acknowledgement that you've received it, I then have, if I need to make sure it gets through, I'm now handling a lot of the logic of retries and all those sorts of things. But what message brokers will do for you is they'll do that for you, and they've hopefully been written by people for whom this is their full-time job, and they can do a good job. And there are lots of excellent message brokers out there. RabbitMQ is great, Kafka is great, there's lots of great ones out there. But this is now as beneficial. We like offloading work to smart people. We do it all the time with databases. Some of the smartest work in the world has been done inside databases. We get a database, we just use it, and it works. Message brokers can be the same. I'm offloading a bunch of concerns to you. Great, fantastic. There's a few people actually chimed in that for them, asynchronous communication was very much around this idea of the broker. Here's someone saying that for them, asynchronous communication is like dropping a mail in a red postbox. then going on with your life. And then one day, boom, Postman Pat stuffs something into your house mailbox along with the millions of coupons and charity mailers. Now, I do appreciate that some of you are local, some of you are not local. This is an international conference, which is part of the reason I like doing NDC London every year. So I should interpret a few things. This is Postman Pat, right? This is the OG Postman Pat, the old stop animation one. I think there was a newer version that might have been like computer generated that had a hovercraft and stuff. This is the proper Postman Pat, right? Works as Village Postman. The idea that you know the name of your I actually do know the name of postman where I live, but that's a different thing. When I do this talk for the US audiences, I have to explain that we also have letterboxes in our houses, right? People go up, they post in your letterbox, right? And this is a useful property. The postman brings a letter, they put it in your letterbox. I don't have to be home. When I get back home, the letter will be waiting for me. Whereas in America, of course, people are not allowed onto your property because if you do, you'll shoot them dead. So instead you have like these mailboxes, right? Now, actually, these intermediaries, there are different variations. I talked about the message brokers being the most common one, and I mentioned RabbitMQ and Kafka. Although they're quite different to each other, they're both very much message brokers, used for different purposes, different trade-offs, right? But there are other things that we can use as intermediaries without, we may not realize we're doing it, but we do all the time. We often communicate via a database, okay? You can put something in, one service can write something to a database, and a different service later on can read something out of a database. It's probably not a good approach as a general purpose because of all the coupling issues that occur, but people do this. The database itself is holding on to the information before the next thing uses it. File systems. All those mainframes that still run a lot of our banking systems are mostly communicating, passing files around. There, they're using the file system as an intermediary. I put a file there, and you get the file later on. You can even use email for this purpose, right? You could use email for communication between services. But don't do that because it's stupid, right? But the key thing with this idea of decoupling, of this temporal decoupling, is that the sender of the message doesn't need to worry about whether or not the recipient is currently available. I may still want to make sure it does happen. I may still want to know that this has been received and handled appropriately, but if in this exact instant the recipient isn't available, that's okay, because we've got an intermediary that's going to deal with this for us. Now, of course, for this to work, you need to trust the intermediary. This is why you'll have conversations about how well run your message broker is. There's reasons I will never use ActiveMQ, right? It's scars of the past. I'm sure it's fine now, but like over a decade and a half ago, ActiveMQ hurt me, and I will not go back. This is also why certain databases are good, and this is also, we have to trust, right? There's a degree of trust. We place it in the same way that we put trust in the faith of the people that create our database and run that database for us. So this is interesting. So let's explore this in a bit more detail. Let's look at it in the context of request-response-based communication then. This is often the confusion I think people get. They sort of see how message brokers can be used for events. That's pretty straightforward. But how does that work for request-response? Let's run it through. So here we've got a service A, and service A wants to send a request to service B. So it takes that request, and it goes to the broker, and in this case here, there's going to be a dedicated queue. This would be the request queue for service B, and I'm putting items into the queue for service B. Now, if service B is available straight away, it can pick up the work. Maybe it's busy at the moment, doesn't have a spare thread, but when it does, it will pick up the work out, and I take that work from the queue, and I can start working on it. So here, B has picked up that request. Now we've got a response, haven't we? I've done the work, it's worked, or it hasn't worked, I've got to send back the response. So how do we get the response? It's the same again. I put the response into a response queue, and we receive the message at the other end. Request response via a message broker. Of course, it's not actually that simple. If it was, this would be a shorter talk. Because in reality, I'm drawing this sort of a semi-logical architecture diagram here. There's a box called A and a box called B. But in reality, when we deploy A, when we deploy B, there are going to be multiple copies of them. We often will have multiple instances of a service to accommodate for nodes dying or to maybe provide the scale that our system needs. So let's tweak this a bit. Let's now imagine we've got two instances of service A. The first instance of service A sends that request. B generates a response, and it comes back into the queue, but we cannot necessarily guarantee that the same instance that sent the request can handle the response. Now, there's one or two things you can do at this point. There are two trouser legs of possibility. Down the first trouser leg of possibility lies doom. Down the second trouser leg of possibility lies, this analogy is not going anywhere good, but it's better. There's one good trouser leg of possibility here. So a lot of people at this point will say, no, it's fine, we'll solve this. We will make sure that that response is somehow routed only to the instance which sent it. And there are ways you can do this, right? This is effectively, though, like trying to do sticky session load balancing. It is technically something you should do, but it is not something you should do. Why is it a problem, Sam? Well, look, if I have put in the complexity in the system to ensure that the response goes back to the instance that sent the request, and I could do it with some correlation IDs, that's not a problem, I could do that easily enough. What I'm basically saying is only that instance of the service can handle that response. Now, that might be because you're holding on to state in memory, and you're effectively like persisting the request-response flow in memory, and you want to carry on your processing. What's the issue with that? What happens if that original instance of A dies? Now, if you implement this such that any instance of A can process the response, so we actually have stateless processing of the response, guess what? You don't need any of the complexity about routing the message, and any instance of A can serve as a response, and you can shut down and spin up nodes willy-nilly to handle the load really easily, and that's a nicer way of working. This is effectively stateless processing of the responses. This is exactly why you shouldn't do sticky session load balancing, and you shouldn't build stateless services unless you really, really, really need them. And look, if you think you really need stateless processing, you probably don't, and if you really do, you know enough to ignore me anyway. So, this actually I think is quite useful. So actually, when people start getting into this world, I think it's a useful forcing function because it forces people to think about failure and actually encourages stateless processing when you start using brokers for request-response flows. These things aren't necessarily evident, though, of course, when you're running just on a laptop, but just ask yourself some questions. What happens if this dies? More to the point, what does happen if a computer dies part way through processing? If we come back to our non-blocking code from earlier, here, by design, we assume the responses are coming back to the same piece of code. We've got a bit of client code running. I've got a process. I'm asking you to do things. They're coming back to me. So in this example, we do expect all the responses to come back to the same instance. So if it does die halfway through, we've got to work out how to deal with that situation. Honestly, most of the time you deal with this by retrying. If you make operations idempotent, retries are safe. Making operations idempotent is another talk I could probably do some other time. But I think it's arguable, though, that the use of intermediary-based communication does actually encourage stateless processing. And I think, in general, encouraging stateless processing of request, response, and events is a much happier place to be. You can still put stuff in a database, that's fine. So we've got some different definitions out here, right? We've got for some people, it's about immediacy. For other people, it's about removing temporal coupling. For others, it's about non-blocking. For some people, it requires that they have an intermediary. But these are all fairly explicit terms. We know what these things mean, or at least we can have a more detailed and accurate conversation about them. But when you say the word asynchronous, all of these terms are flying around in people's heads. So, does it matter, though? Words have different meanings. Many of you, English is not your first, it's maybe your second, third, or even fourth language. And I suspect even for those of you in English, you appreciate the fact that in words, I only speak one language. Yeah. I speak English just. Words within English have many different meanings. Does anyone want to guess for me which word in the English language has the most dictionary meanings? It's set. So in the current edition of the full Oxford English Dictionary, the word set. Get is close behind, which I think is quite nice from a programming point of view. Now, in the latest edition that they're working on, that I think is going to be ready for the mid-2030s, this is, it's a big thing. It's like a multi-volume thing. That's probably the word we think is going to have the most definitions now. Set has 430 different meanings in a dictionary. Run, at the moment, well, as of 2011, had 645 meanings in the current draft. Could you list them all? No. Can you use set and run in your daily lives? Yeah. So why am I bothering with this? Words have different meanings. We just deal with it, right? It's fine. It's not a problem. So why am I going on about asynchronous things, different people, and that is a problem? The issue is that we derive meaning of a word via the context in which the word is used. So I was actually having a conversation with Ian Cooper at this conference last year, and we were having this conversation. And Ian is a lovely guy, and many people have a hinterland. Ian Cooper's hinterland is the Alps. There's all sorts of things he's done in his past and in his present. And it's unsurprising to find that Ian studied something called semiotics at university, which is the study of meaning. And he was explaining to me, well, what's happening here is that the meaning of a word becomes more narrow as we add other words around it. So when we look at a word in isolation, when we put other words around it, the meaning of that word becomes much more clear. So let's take an example. I want each of you to think, what does the word run mean to me right now? Just the first thing that comes to your mind. So now I'm going to put some other words around it. And let's see if what I thought run meant is the same thing as what you thought run meant. The issue got worse the moment the program was run. There's a possibility we were using the same definition of run, but maybe weren't. Let's try again. Pick a different meaning or a different way in which you'd use the word run, and think of that. Oh, the economy crashed due to a run on the banks. It's a different way we could use run. Now, if I just said run to you, actually, if I just said run, you'd go, If I said run, the context there is, there's context there in the pitch and the way I'm delivering it. But in here, there's no ambiguity, or there's much less ambiguity about what a run on the banks means. Context is important. The context in which we use words is important. Let's come back to the Reactive Manifesto. Think about context. They talk about asynchronous communication in the context this manifesto means dum-da-dum-da-dum. The first sentence in this section is that the Oxford Dictionary defines asynchronous as not existing or occurring at the same time. Now, indeed, if you type in what does asynchronous mean into Google, this is the exact answer you get back. This is not the definition of asynchronous in the Oxford Dictionary. It is a definition of asynchronous in the Oxford English Dictionary. The dictionary actually understands the importance of context. It's very easy if you're British to get access to the full Oxford English Dictionary. It's all freely available at libraries, and you get free logins to use it online. My brother is a medieval historian, and he also has access, so he gave me this page. These are the full definition of asynchronous in the Oxford English Dictionary, and it's a long, long page. And actually, the first definition that comes up is basically the top one in the Oxford English Dictionary. No surprise, Google gives you the first hit, which is probably why it's ended up in the Reactive Manifesto and has been requoted ad infinitum. Now, interestingly, talking about context, where did this definition come from, the one that everyone seems to want to use? Originally only in medical contexts. So this is a term that came from a medical context, not a computing context. So does the Oxford English Dictionary have anything to say about a computing context for asynchronous? Yes, it does. In fact, there are two definitions of asynchronous in computing. The one that's closest to what we're talking about is the first one here, which states that designating transmissions in which packets of data are sent at irregular intervals, with the start and end of each packet being marked by specific signals involving such transmission. I don't know what that means. I suspect this is discussing the asynchronous communication from the point of view of somebody implementing a low-level networking protocol. So the context here of this definition is much more precise than the one in the Reactive Manifesto, but still useless and not helpful. Why am I going on about this? Fundamentally, software is a type of socio-technical system. Okay. Socio-technical. Socio, people. Technical, technology. Technology in the broader Latin sense of the word technology, techne, right? Complex systems. When we build software, it's these things coming together that create the things that we build. Now, before you start thinking, oh God, he's going to come over like some sort of snowflake liberal. Yes, I am a snowflake liberal, but I'm also correct in this one, right? The concept of socio-technical systems actually comes from studies of coal mining. There's actually the context, the work around socio-technical systems actually done by the Tavistock Institute here in London. If you want to, there's a great rabbit hole you can go down where the Tavistock Institute, which came up with the concept of socio-technical systems, is basically the center of a really elaborate conspiracy theory where certain people think they're trying to control our minds because it's their fault we've got the Beatles and the Rolling Stones. It's a weird, deep rabbit hole to go down. Anyway, I digress. But the concept of this is like, so they were looking at, look, we've got these complex things happening, coal mining. We've got people. How do we make sure all of this stuff works together and operates together? Software is one of those things. The creation of software is about people working together to construct something. The amount of useful software created by individuals is vanishingly rare. Some people say, Linus created a kernel. Linus created the first version of the kernel. His biggest contribution was creating a community to contribute to it. There are very, very few things where one person created it, software-wise, by themselves that you use day in, day out. I'd say virtually none. We bring people together with complicated systems to build things. To be able to do that, it means we need to be able to work together and communicate to each other. You may not believe, that this is that important, but think how many times have you had a conversation with somebody only to realize you're talking at cross purposes. We're going to make the system asynchronous. You're thinking about it in terms of a phone call, they're thinking about it in terms of an email, you're both using the same word, but you're on the different page. And when you have that kind of misunderstanding going on, problems can occur. You don't have to take my word for it. There's a little thing called the Old Testament. So, the Old Testament is quite exciting. There's lots of good stories in the Old Testament. And one of those stories is the Tower of Babel. It's actually a very, very short section in the King James translation of the Old Testament. And it tells the story of these people who are building a grand tower. And actually there were two reasons cited by how their tower could be grown in such a magnificent fashion. One is because they spoke with one language. And the ability to speak with one language aided them. It also mentions that they basically had good concrete, which often gets exposed, they had good technology as well, that's put off to one side. But they could speak, they could talk together, they could communicate to each other. Now, no rationalization is necessarily given in the Old Testament as to why what happened next happened, and there's lots of interpretations. But basically, the Old Testament God said, no, don't like that. And he basically made them all speak of different languages. And the tower, lo and behold, could not be completed. So this is a story which is several thousand years old about the understanding of if we can all speak the same language, it's much easier to do grand things. It also it's another one of those stories which says that the Old Testament God was sort of quite different to the New Testament God. It's like one of those weird sort of character arc changes, we don't need to get into the last season of Game of Thrones, but we all know that certain characters had really weird changes in their character arc happened halfway. But anyway, that's a different problem. I really don't want to get into an argument with people about both the Old Testament and the last series of Game of Thrones, because we've all got a long day. Look, this is an old story. If we think about our new story, the term asynchronous. The term asynchronous, in the context of interprocess communication, has so many meanings to so many different people, the word itself effectively no longer has meaning. It is not a useful word for us to talk about. It doesn't help us achieve anything. So what can we do? As always in these things, start by understanding what your application needs. Think instead about how your application wants to handle different situations. How quick do you want the communication to be? What should happen if the server I'm talking to is not there? What should I do if a client crashes? Decide how you want your application to behave. And then use some of those more specific terms that we talked about today. Be more explicit. Don't say our system is going to be asynchronous. Say clients should be non-blocking, and here's how we're going to do non-blocking clients. Say that you want to, where possible, run operations in parallel and explain why. Say you're deciding to use a broker as an intermediary. Be more explicit. That will aid communication. You'll be on the same page, and you'll be better able to build things together. Try not to make this all about correcting what somebody else thinks these words mean, though. I mean, the clickbaity title for this talk obviously comes from The Princess Bride, where the joke that we're all in on is that Vinicus is using the word inconceivable. And we as the audience, and especially Inigo Montoya, know that he's using that word incorrectly. Right? You keep using that word. I do not think it means what you think it means. This is a bit different in a working environment. When someone says, I want to make this asynchronous, don't think I know what that means better than you. Just ask them, what does it mean to you? What does that word mean to you? Get a bit more explicit about it, because if you can communicate more clearly, you'll build better stuff together. And what you find might shock you. All right, thank you very much. We've got about 7 minutes for questions. If you do have questions, there is a microphone to the left-hand side. So if you're able to ask, if you want to ask a question and you're able to get to the microphone, that'd be appreciated. Has anyone got a question for me? You want to ask? Okay. Well, if you're too scared, I'm going to hang around here for a bit. If you want to find me online, I'm not really on Twitter much anymore for reasons I won't go into, but you can find me on Mastodon over on the Hachyderm server. But other than that, I hope you have an amazing conference. This is one of my favourites. And if you are visiting the city, do take time to explore the area and have a nice time. The weather at the moment seems to be keeping you, it's not raining right now, so enjoy it while it lasts. But thank you so much.